Remember the example from the very first part of the series? Your friend opened a restaurant in a city with light traffic where delays from congestion are almost non existent. The restaurant gets multiple food orders from customers at different locations. There's just one delivery person who delivers all the orders in a single trip and then returns to the restaurant. But here's the problem, your friend isn't happy with the total delivery time. She believes that if the delivery person follows a smarter route, the overall delivery time could be reduced. She thinks a program can be created to suggest the shortest and fastest route. Sounds simple, right? But as we will see in this final episode, this seemingly practical problem is actually one of the most famous NP-complete problems in computer science, the traveling salesman problem. So she asks you to design an algorithm and build a mobile app. The app should calculate the best delivery route every time new orders come in. She is even willing to pay you for this service. Sounds like a great opportunity, right? But before you start coding, here's the big question. Can you actually design such an algorithm that always gives the best route efficiently? That's exactly what we are going to explore in this final part. You've understood the challenge. The number of food orders and customer locations will change every time. You'll be given the list of customer locations and all possible routes with their distances. As you think about this, you realize something. This problem can be represented as a graph. Each customer becomes a node. An edge connects two nodes if there is a direct route between those customers, and the weight of each edge represents the travel distance or time. With this graph model in mind, you are ready to start thinking about how to design an algorithm to solve the problem. After spending a lot of time analyzing the problem, you realize something critical. The algorithm would require an exponential number of steps to find the best route. This means that if the number of orders grows large, it could take years or even longer to compute the exact solution. At this point, you have already invested a lot of effort. You understand the problem inside out. This problem is so hard to solve efficiently, and you need to explain to your friend why. Luckily, you have just learned about NP-complete theory. So, to demonstrate that this problem is computationally hard, you will follow these steps. First, you need to show that this problem can be represented as a graph. However, this is an optimization problem. Our goal is to find the route within the minimum cost, starting and ending at the restaurant. But NP-complete theory applies to decision problems, not optimization problems. So, we convert this into a decision problem by introducing a threshold value k. The revised problem now becomes, is there a route with a total cost less than k? We will call this problem Q. The answer to problem Q is either yes or no, making it a decision problem. If we can prove that Q is hard to solve or intractable, then the original optimization problem is also intractable. Now, following the trick we discussed in the last video, our first step is to prove that this decision problem belongs to the NP class. To show that Q is an NP, we need to demonstrate that any yes instance of the problem can be verified in polynomial time given a certificate. The certificate is nothing but a proposed solution, an ordered list of the n customer locations. This ordered list represents the proposed tool. To verify it, we calculate the distance between each consecutive pair of locations in the list, and then sum these distances. This calculation takes order of n time. Next, we check whether this total distance is less than or equal to k, which takes constant time in the usual computational model. Since all these steps run in polynomial time, the verification process is efficient. Therefore, our decision problem Q belongs to the NP class. Now, following the trick we discussed in the last video, the next step is to find a problem R that is already known to be NP-complete or NP-hard. Then we need to demonstrate that R can be reduced to our problem Q in polynomial time. Now let's talk about the traveling salesman problem. It states, Given a list of cities and the distances between each pair of cities, the task is to find the shortest possible route that visits every city exactly once and returns to the starting city. To visualize this, consider a graph with 4 vertices and 6 edges. In this graph, we can easily find the shortest route, but this is just a small example. When the number of cities grows, the problem becomes extremely challenging. The decision version of the traveling salesman problem asks a yes no question instead of finding the exact shortest route. It says, given a graph, does there exist a route that visits each city exactly once, returns to the starting city, and has a total cost less than or equal to k? Here, k is the cost bound. For example, if we take this graph and set k equals 6, we give the graph as input and the output will be yes if such a route exists and no otherwise. In this example, a valid route does exist. Walk through our decision problem queue again. It states, given a set of house locations and distances between them, does there exist a route that visits each house exactly once, returns to the restaurant, and has a total cost less than equal to k? Here, the restaurant is both the starting and ending node. Now, compare this to a decision version of the traveling salesman problem, which says, given a set of cities and distances between them, does there exist a route that visits each city exactly once, returns to the starting city, and has a cost less than equal to k? So, what's the difference? In our problem, the starting node, that is the restaurant, is fixed, while in TSP, the starting city is not fixed. The route can begin anywhere, but if we remove the constraint that the restaurant must be the starting node, our problem becomes exactly the same as the decision version of traveling salesman problem. Now let's think about this. Suppose we have a traveling salesman problem route that starts from node 2. Since the route forms a cycle, it can start from any point without changing the total cost. Rotating a cycle does not change its length. That means if we say start from the restaurant, visit all houses exactly once, and return to the restaurant, the problem does not fundamentally change. The same route works as the solution for our problem as well. So, what did we just demonstrate? Our problem is essentially the decision version of the traveling salesman problem. In other words, the decision version of traveling salesman problem is polynomial time reducible to our problem. Since the decision version of traveling salesman problem is NP hard, our problem is also NP hard. And because our problem is also an NP, this means our problem is NP complete. And here's the key takeaway. If the decision version of our problem is NP complete, it clearly indicates that our original optimization problem is also computationally hard. With the knowledge of P, NP, and NP complete, you can now reason that while this problem may not be provably intractable, it is widely believed to be so. But does that mean you give up? Absolutely not. It means you shift your goal. Instead of chasing an exact optimal solution, which may take an impractically long time, you now focus on designing an algorithm that runs in polynomial time and gives a near optimal solution. When time or resources are limited, this trade off becomes not only practical but smart. It's a win win, efficient computation with acceptable results. In short, understanding how to prove NP completeness helps you recognize which problems are likely intractable and where to stop searching for exact solutions. Instead, you start exploring approximation algorithms, heuristics, or other alternative strategies. That's how theory guides real world decision making. That's a wrap for our NP Completeness series. We began with simple questions and ended up uncovering one of the deepest concepts in computer science, NP Completeness. If you have followed along, you now understand P, NP, NP Complete, and why some problems are so incredibly hard to solve. Remember, theory isn't about giving up, it's about making smarter choices. Sometimes the best solution isn't perfect, it's a good approximation that works in the real world. If you found this series helpful, don't forget to like, share, and subscribe for more deep dives into computer science. Until next time, keep learning and keep questioning.